The broadcast is now starting. All attendees are in listen-only mode.
Welcome to Greenlight on Lidar, Developing Low-Cost Systems for Autonomous Vehicles, a webinar presented by Zemax and hosted by Photonics Media. My name is Robin Riley, and I am the Photonics Media web editor. Our speaker today is Sanjay Gangadhara, CTO and Director of Research and Development at Zemax. Sanjay will be speaking today on the factors critical to solving the LiDAR design challenges that engineering teams face. If you have any technical issues during this webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout this presentation. Just type your question in the question box to the right of your screen, and we will answer as many as possible at the end of the session. If you are interested in receiving a copy of the presentation, please email the moderator at robin.riley@photonics.com. And with that, I'd like to turn the presentation over to our speaker, Sanjay Gangadhara.
Well, thank you, Robin. I appreciate that. As Robin mentioned, I'll be talking today about the development of LiDAR systems for autonomous vehicles and really the role that virtual prototyping plays in the evaluation and development of those systems. I wanted to also at this time acknowledge my colleague, Sandrine Oriol, who contributed a lot of content to this presentation, but isn't able to join us today. So just starting with a brief outline of what the talk's going to be covering, I'll start with an introduction, which will cover what LiDAR is and how it's being used in a variety of industrial applications in the scientific and commercial spaces. I'll then move on to talk about how LiDAR would be used inside of an autonomous vehicle and what some of the challenges are with implementation of LiDAR systems in autonomous vehicles. One of the main points that I want to emphasize as a part of this talk is that there isn't a clear-cut solution that's applicable for all applications or all types of systems when we talk about using LiDAR in autonomous vehicles. So really, we're still at a state where we're making design decisions and making trade-offs between designs as we look at what the appropriate system is for any particular autonomous vehicle. And so I want to talk a bit about what drives some of those choices, what are some of those technical considerations that we have to think about when we're designing a LiDAR system, and how we can evaluate those choices and make those trade-offs using virtual prototyping, being able to quickly and efficiently use simulations in guiding the best design decisions that you want to make for any particular application. We'll look at this actually through two simple but specific examples using the Zemax virtual prototyping software solutions. And then for one of those examples, we'll do a little bit of a deeper dive and look at the as-built performance and how as-built performance would affect the results that you would get from a LiDAR system. And so this is accounting for things like environmental effects on the system performance, optical tolerancing, so the manufacturability of the optical components and how that would affect the performance of the system, as well as starting to evaluate the impact of mechanical design on the system. I'll finish up then by talking about my thinking on next steps for LiDAR systems that are used in autonomous vehicles, and then provide a brief summary. So what is LiDAR and how is it used more generally? Well, LiDAR is just a method that uses light waves to determine the range or the distance to an object. It's very similar to radar that's been around for a long time, but instead of using radio waves, we're now using light waves. LiDAR is commonly used in a variety of applications. These include the automotive industry, and as we'll be talking about here specifically in autonomous vehicle designs. But it's also been used with commercial robotics, inside of construction or industrial environments. As a tool for geographical survey, this is maybe one of the more common applications that users may be familiar with. And as we see here, this is an example of a topographical map that's been generated by the U.S. National Park Service using a LiDAR system. In a variety of military applications, and then finally also in commercial transportation, so trucking, railway, etc. So LiDAR has been around actually for quite some time, but one of the key points that I want to make is that in many, if not most of these applications, the solution that's been implemented has been a custom and expensive solution. So it usually tends to be something that's very application specific and therefore at a high cost. And so one of the goals of virtual prototyping is to be able to come up with a solution that is low cost, that can be mass produced. Now, what would the role of LiDAR be in an autonomous vehicle system? I think we want to start by defining what we mean by autonomy. So there are international standards which do just this, and they define autonomous driving range from a level 0, which indicates full driver control, so there's no automated assistance whatsoever, to level 5, which is full autonomy of the vehicle, in which the vehicle performs like a human driver under all conditions. Now, LiDAR is a critical component for reaching this level 5 autonomy, as we'll talk about here in a moment. But it won't be the only component that's required to reach level 5. So to reach this full autonomy that's required for level 5, we really need a variety of systems. These include short, medium, long-term radar, or long-range radar, I should say, as well as visible camera systems, ultrasound systems, and LiDAR systems. As you can see in this diagram here, where LiDAR is thought to be most effective is really in this intermediate range of detection for the vehicle, where we're interested in collision avoidance, in pedestrian and obstacle detection at ranges that are typically 50 to 100 meters, or about 100 to 300 feet, something in that range. Now, within that range, LiDAR provides the most precise sensor technology that we have available. It has significant advantages over camera and radar within this range, really resulting from the short wavelengths that we're using when we're using light waves for the range detection, as opposed to longer wavelengths that are used by radar systems. What I've shown here now, and I'll play a video here shortly, but it's just a basic example that's been built up within the Zemax Optic Studio software package to illustrate the concept of how a LiDAR system might work. And this is an example of a pulsed scanning system. And what we have here is basically just a light beam that's being illuminated from a system that's on a vehicle, as shown here. It's going to go, that light beam is going to be scattered off of a target that's in the far field with a pedestrian in the way. And by looking at the path length, which corresponds to the time that the light travels as it goes from the source out to the wall, we can get an indication of the obstacles that are between the light and that target. Now, LiDAR systems, as I'll talk about a little bit later, actually are a bit more complicated than this, but I wanted to just show this as a basic example. And so what we've done here in the software is we've just set up a simple source where we can scan that source, and you can see that scanning occurring here as the beam is moving across the target. And we can then measure the distance that beam travels as it scans. And we can do that now in a two-dimensional fashion using a tool within our software that's called the universal plot. So it allows the user to define a two-dimensional scan of this beam, and in this case we're doing that over both the horizontal and vertical direction in a range of about 2 meters, 2 to 3 meters in each dimension. And then having done that, we can look at the path length that the ray travels as the ray propagates, and we'll see that path length is affected by the obstacle that's in the field of view of the beam as it's going to our target. So you can see here actually the outline of the pedestrian shown by this simple analysis. And so this is a very basic analysis that shows how that LiDAR system can work by looking at the path length or the time of flight of the beam as the beam is propagating from the source out into the far field. Now, what are some technical considerations for using LiDAR in autonomous vehicles? The first is that the systems need sufficient range to be able to capture information about traffic that's traveling in different speeds across the full field of view that's of interest. And this requires that these systems have accurate measurements that have good resolution in the transverse direction, so kind of in the perpendicular direction, but over the full horizontal and vertical field of view. And so by horizontal field of view, we really mean that we want to be able to scan this full 360 degrees relative to the driver position, so that the LiDAR system should be able to see both in front and in back and along all sides of the driver. And we want usually to have a field of view in the vertical direction, or basically along the line of sight of the driver, in the range of about 20 degrees, usually starting from just a little bit above the driver's line of sight down to about 15 degrees or so below that line of sight is a typical vertical field of view that we require for the LiDAR system. And what we're looking for in terms of resolution is going to be then much smaller than that. So we're looking for the ability to detect objects or obstacles in that field of view with a resolution of anywhere from a fraction of a degree up to a couple of degrees. So something that could be maybe an order of magnitude or smaller relative to the full field of view that we're trying to capture. To translate that into numbers, for an object that might be 20 meters or about 60 feet away from the driver, we're looking at being able to detect objects that are about 7 centimeters in size. Now, we also need this data quickly, right? Because the scene that the driver is seeing is changing as traffic is changing, as the vehicle that the driver is in is moving itself. And so we need to be able to have a fast refresh of these results that are based on the speed of the vehicle and the surrounding vehicles. The scanning speed, the speed of the light source itself will determine then the resolution and the accuracy of the LiDAR system, and the distance of the source to that target. Now, some other technical considerations that we have when we think about LiDAR systems in autonomous vehicles are that these systems have to have robust performance in a variety of environmental conditions over the full lifetime of the system, right? So we need to make sure that we're collecting enough light from these various obstacles that are in the field of view, and that we can do so independent or even as weather changes, as the background conditions change, for example, the amount of ambient sunlight that might be incident on the system, etc. And again, as the detector is aging over the full lifetime of the detector, which may be of the order of years, depending on how long or what the life cycle is for replacement of these systems on the vehicle. Now, what I want to show here is just a schematic that shows in a little bit more detail how some of the fundamentals of how these LiDAR systems would work, really starting with the transmitter component or the lighting component. So this is the light source that's going to illuminate the field of view and tell us what's out there in front of the driver. What we are going to have then is that light hitting the targets or hitting the objects that are in the driver's field of view and being scattered back then to a detector that's back on the vehicle itself. The amount of power that's received on the detector will depend on how much power is, of course, on the target itself, and the power that reaches the target will depend on factors such as the power of the laser, how much of that power can be transmitted through the atmosphere, which will be a function of the atmospheric conditions such as weather, and the size of the beam that we can achieve on the target. And so the tighter the beam that we can make on the target, of course, the more power that we can deliver on the target, but then we also need to ensure that we're getting a high enough resolution to be able to capture all the information about the target that's of interest. And in order to optimize for that beam size on the target, we often then provide optics in front of the transmitter, so between the laser source and the target, to provide the right beam profile on the target itself. The amount of power that then reaches the detector or the receiver will depend on the reflectivity of the target, as well as the distance from the target to the receiver. So this is where we get information about the ranging itself, and the detector size, and the solid angle, so how much light can be collected in this cone by the detector. And that solid angle can be increased by placing optics in front of the receiver. So we often, in addition to having an optical system in front of the transmitter for optimizing the beam size on the target, we're also going to be designing an optical system in front of the receiver to increase or to optimize the collection of light on that receiver. Now, with these systems, another consideration, of course, is going to be safety, and specifically we can think about eye safety for both the pedestrians and the drivers that are involved in the scenario. And this limits the choices that we have for the laser sources in terms of both the power and the wavelength that these sources can be at, which can then have an effect on the range that these sources can work at. And then finally, of course, if we want to deploy these in mass, we need these systems to be low cost. We want the expense to be an incremental addition to the cost of the vehicle and not the driver for the cost. And so part of the exercise here is to be able to come up with the best design and identify the best trade-offs to drive the cost down as much as possible. Now, in doing so, as I mentioned earlier, there hasn't been a clear-cut solution or a clear-cut winner that's been identified. There's still a lot of players working on a lot of different solutions throughout the industry. A lot of different technical solutions that involve the sources, different types of sources, different types of wavelengths, different type of detectors or sensor technologies as well. And so I'll talk a little bit about some of the design options which are available for LiDAR, and these can include the mechanical configuration. So whether you want to have a scanning laser or a fixed system, the wavelength that we use for the laser, as well as whether we use a pulsed system, as I showed in my simplistic example earlier, or whether you want to have a continuous wave laser model. And we'll talk a little bit about the pros and cons that are involved with each of these design choices. So starting out with looking at mechanical versus flash systems. So what we call a mechanical system, and in this webinar what I'll be referring to as mechanical, I'll also interchange with the scanning system. This is a system where you have basically a laser, a single laser on the vehicle that sends out a short pulse, and we're going to then look at the time it takes for that pulse to hit the targets in the field of view and return. So it's a time of flight type of a measurement. And then in order to capture data over the full field of view, we're going to scan that laser in the 360-degree arc around the top of the vehicle. Now, the advantages of these scanning systems are that you can capture that full field of view with a single system. And these systems generally work at high resolution, so you can get a very good accuracy measurement from these mechanical scanning systems. The disadvantages of a scanning system are that they include mechanical moving parts, and so they tend to be more expensive, and they are more sensitive to things like wear and tear, misalignment, optomechanics, things of that nature. So those are issues that you need to be concerned about with mechanical systems. Conversely, with a flash system or a solid-state LiDAR system, these are systems where we have an array of diodes on the vehicle, and in which each source in the array generates a line scan, in which we capture actually a large part of the field of view through a single pulse. Now, we can't capture the full 360-degree field of view from a single source in this case. Usually the field of view is in the range of about 40 degrees in such a scenario. But with a single pulse, we can get that full 40-degree information from that pulse. Now, in order to obtain data over the full 360 degrees, there are a couple of different options. You could scan this single unit, which again would make it more like a mechanical LiDAR system. But it's a case where you don't need to do as high of a scanning frequency because you're capturing a lot more information about a bigger chunk of the field of view at once. You can actually scan at a lower frequency to obtain that information, and so you may be less sensitive to issues of wear and tear or optomechanics in that case. Another option is that you could actually place multiple units on the car itself to look at different parts of the field of view. And so that would allow you to build a system that has actually no moving parts at all, but the complexity then is added by having multiple units working simultaneously. Now, again, the advantages of a flash system are that the systems themselves tend to be at a lower cost per unit, with the trade-off being whether you choose to scan an individual unit or employ multiple units on the system. But the disadvantage is that you tend to sacrifice some resolution in these systems. So the resolution, the transverse resolution that you can obtain is generally about an order of magnitude larger than you would have in an equivalent mechanical system. But generally still good enough to capture information about objects of interest in the field of view. Now, another design decision that you can have in a LiDAR system is what laser wavelength to use. And there's two common choices that we have for wavelength in these systems. The first is at 905 nanometers, so this is closer to the visible, kind of in the near IR. The advantage of these wavelengths are that you get much better transmission in the atmosphere, so you'll get more power returned to the detector and therefore a higher signal to noise. And with these, you can use traditional silicon-based photodetectors, which can be purchased and implemented at lower cost. This is just some data which speaks to the first point about transmission. So the transmission through the atmosphere is generally going to follow this kind of an exponential relationship where there's going to be a dependence on the distance to the target as well as an atmospheric extinction coefficient. Which then will be a function of wavelength, and it will be a function of course, the atmosphere, the weather conditions as well. But you can see from this plot here, which shows a plot of the atmospheric extinction coefficient as a function of wavelength, that this value is much smaller, or is smaller at smaller wavelengths, and increases as you go to higher wavelengths. And of course, a smaller value here corresponds to higher transmission, and so therefore, the lower wavelengths do give you better performance in terms of transmission. Now, the disadvantage is that the eye tends to be more sensitive to these lower wavelengths, and so you do have concerns with eye safety. And so as we go up to higher wavelengths, up at 1550 nanometers, this is where you have better support for eye safety. You have less probability of that light coming back and hitting the corneal region, or the retina in the back of the eye, I should say, and therefore you can use higher power lasers at this higher wavelength because you have less of that light, which actually makes it back to the vulnerable retina in the back of the eye. The other advantage of using the higher wavelength is that there tend to be lower levels of ambient light or background light at these wavelengths, so you don't have to worry about noise coming from sunlight or other environmental light sources contaminating the detector signal. Now, one of the disadvantages of using the higher wavelength is that this requires non-silicon photodetectors, but there have been some advances made recently in the use of avalanche photodiodes that have high efficiency that can be used to capture light at this wavelength. And so we are seeing an industrial shift of LiDAR systems to moving more towards these higher wavelengths as a result. And then one of the last things that I wanted to talk about in terms of design decisions is the pulsing method for the laser. Whether you use a pulsed light source, as you have in more of a traditional time of flight measurement that you would use for LiDAR, versus a continuous wave model. And what I'll show here, just kind of schematically on the right, are what we mean by these two models. So if we look at our time of flight measurement, this is a situation where we're sending out a very short pulse of light, and we're going to then have that light reflected, or scattered, I should say, off of the target, off of the obstacles that are out in the field of view. That light will be scattered in a variety of different directions with lower energy in each of those directions. And then some of that light will come back to the receiver that's on the LiDAR system on the vehicle, and looking at the time that it takes for that light to return gives us information about the distance to the target. Now, with these systems, you need to have a very short pulse. That's really the key. So the size of this light pulse needs to be very short. You need to have a very fast rise time in order to get accurate information, in order to get the types of resolution that you need. You often need to have optics in front of the illumination source as well as in front of the detector in order to maximize the signal, as I talked about in one of my earlier slides. And then you need high-speed electronics to be able to capture this information over the types of timescales of interest. Now, conversely, another method is one in which you could send continuous waves out of light out into the field, and then use basically an optical mixing methodology in order to detect the signal. So this is a situation in which you are having a continuous amount, or continuous wave, I should say, of light being sent out. That light, again, will hit the objects or the obstacles in the far field, be scattered from those obstacles, and then come back to the detector. But we're not just looking at the detected light itself, but we're looking at the coherent sum between the detected light and the outgoing light to extract information about the range and the size of the objects that light hit. Now, this method has a lot of advantages. One of the advantages is that you can reduce the need for illumination and collection optics in the system, because really what you're looking at is just coherent interferometry of the system, rather than trying to collect a small noise or a small signal of scattered light off of these obstacles. One of the other advantages is that with this continuous wave model, you can actually isolate your system from systems that may be on other vehicles. So you can imagine that as LiDAR is employed on multiple vehicles in the field, that one of the concerns is crosstalk between the LiDAR systems that are out in the field. And how do you eliminate that? Well, with this continuous wave model, you have an option, because you can tune the frequencies that are being used on each of the systems to slightly different frequencies, or to unique frequencies that allow you to get a unique signal back, and therefore filter out noise from other LiDAR systems more effectively. Really, the biggest challenge with these systems are a couple. One is that you need to have much higher power systems for these to be effective. So you really need high power lasers, really that start to put eye safety into consideration, as well as just the power of the source, whether or not we can deliver lasers with such high power. The other disadvantage of these systems is that really you need a lot of intensive data processing in order to calculate these coherent sums, in order to get the information of interest for the system. But again, these are all the kinds of design decisions that users need to make as they're, or companies, I should say, need to make as they're designing LiDAR systems for autonomous vehicles. And as I said, there's really no clear choice or clear solution in the marketplace. And so, you know, as we think about what's driving cost, and that's really what the company is thinking about in terms of their bottom line, these are going to be issues like system complexity, performance, what are the system performance requirements, and the ability to get those systems into mass production. And really the most effective way to determine what the right system is for the application that a company may be employing is to use virtual prototyping. And what we mean by that is to be able to use simulation through connected software tools that give you end-to-end information about your design. And this can be through the user interface. This can also be through programmatic investigation of systems using application programming interfaces. But there's a lot of flexibility when we talk about using virtual prototyping and simulation to be able to design these systems virtually, to find what the best trade-offs are going to be for the application of interest. And this plot here is really just meant to show the variety of options that are available as we think about LiDAR systems, and that really the best way to investigate this entire solution space is through simulation and through virtual prototyping. What I'm going to be focusing on now in the remainder of this webinar is just going through a couple of different examples where we'll use the Zemax software tools to look at some systems that you can employ for LiDAR. One will be a mechanical spinning pulse system, as I showed earlier. The other will be a flash solid-state LiDAR pulse. So these are similar systems in that they're both based on time of flight measurement, but they have slightly different specifications that I'll get into some details on. For each of these designs, we'll provide the system setup within the software, as well as evaluate and optimize the performance. And then for the mechanical LiDAR system itself, we'll go ahead and do a little bit of a deeper dive, looking at the environmental impact on performance, looking at the effect of tolerances, and preparing the system for optomechanical design. So this is just an example of the mechanical LiDAR system set up within the Zemax Optic Studio software. You can see the scanning taking place here through this GIF. We're doing just a short scan, not over the full 360-degree field of view, but just as an example, really just over a shorter field of view, just to show how the components themselves would move as we try and scan the system through the full field of view. In this case, the source is just a single laser diode source. That source would be scanned in principle over a full 360-degree field of view to provide information about the horizontal and vertical position of the target, the X and Y, and then the time of flight, the time that it takes for light to go from the source to the target and back, is what gives us information about the distance or the range to the target. Now, as I mentioned before, with these time of flight or pulse systems, we often have optical components both in front of the transmitter as well as in front of the receiver. But we can model within the software. We can actually model each of these optical components separately. So we can have a model for our transmitter optics, where the goal is to generate a collimated beam that reaches the target with a small spot size, so that we can have high resolution on the target. In order to generate this beam, we'll have optics which include both aspheric lenses and prisms. So really want to emphasize that free-form optics play a critical role in the design of these optical systems within LiDAR. In this particular case, we're using prisms that we've taken from the Thor Labs catalog, and so they've been implemented in the software as CAD models. But Optic Studio has the ability to support both CAD as well as native geometries for freeform optics. With this system, we're actually able to achieve a 0.02 degree beam divergence with a beam radius of 10 millimeters. And we can see that data here. So if we look at the amount of energy enclosed within the beam as a function of beam size, we can see that by the time we get out to 86% enclosed energy, we've reached that at a very small with a very small resolution. So we have very high accuracy in this system. The specification actually is an order of magnitude further out, and by the time we get out to our spec requirement, we've reached full energy within the beam. Now we can again separately model the receiver optics in this system, and the goal of the receiver optics is to collect the scattered light that's scattered off the objects in the field of view over that full vertical field of view. The system that we've designed for this particular case just includes standard spherical lenses, so we're trying to keep the cost down by just using traditional components in this case. But even with these traditional components, we're able to achieve uniform performance over a 20-degree full field of view. So again, in this system, we weren't doing a full 360-degree scan. We were just looking at a limited scan. But even so, we were able to achieve a good performance with this two-lens system. And here you can see a plot which shows the beam size received back on the detector as a function of that field of view. So you can see that it's fairly uniform over the field of view. This is showing the half field of view. And again, if we look at this in terms of the encircled energy, so how much energy is captured within the field of view, you can see that really the majority of that energy is captured in the field of view out to a 10-degree half field of view before we see any significant drop in the energy collected at the receiver. Now, in order to evaluate this full system all up, we can combine the transmitter optics model and the receiver optics model into a single model by converting this system into from what we have been using previously in something we call sequential mode in Optic Studio into a full non-sequential design. And so what I show here is just, again, just a schematic of what the system is meant to look like. What we can do is then put together the full system into a single model where we actually also include fold mirrors here in order to model the system scanning. So actually to account for the fact that we would need to capture data over the full 360-degree field of view in this case. And we can see now the detector results that are shown as we look at these different scan angles as we go over the full field of view. one of the most useful pieces of information in putting together the full system into a single model is to look at actually the amount of power that's received back in the system. So rather than looking at the beam size, looking at actually the energy distribution on the detector. And in this case, we're just looking at the results for a single configuration, but looking at a single scan at 45 degrees, where the power of the source is 75 watts, we can see that the power actually is significantly reduced, right? So this is really one of the challenges that we have with LiDAR systems in an autonomous vehicle design, is that while the power of the source may be of order watts, the power that's detected at the receiver is of order microwatts. And so really we have to have high, a very sensitive detection in order to be able to see this signal. For comparison, this is just an example that we've quickly worked up within the Optics Studio software to show how a flash LiDAR system or a solid state system might work. Again, we're trying to capture information over a similar field of view of this system, but in this case, we're using an array of diodes in order to capture that information. Each source within the array will produce a horizontal beam over that full 40-degree field of view. So within a single pulse of that source, we capture information about the full 40-degree field of view. The receiver then focuses light onto a detector array, which provides us information about the horizontal position that the light has come from, and therefore between knowing what source the light was emitted from and where that light falls in the detector, we can then get information about the XY or the horizontal and vertical position of the beam on the target. And then again, this is a system where we're going to use time of flight to measure the distance to the target. And just as we've done for the mechanical LiDAR system, we can break this system up into two separate components that we model in so-called sequential mode of Optics Studio. So the first are the transmitter optics. These are the optics in front of the laser source. In this case, our goal is different than it is in the mechanical LiDAR system. Here we're looking to generate not a small beam size on the target, but actually a horizontal beam, because we want to be able to capture full information in the horizontal field of view with a single pulse. But we still want it to have high resolution on the target, so we still need a small vertical size to that beam. In order to do this, in this example, we're using cylindrical components, but another option could be to use scattering diffusers as well. So there's a variety of options that are available, and either of those options could be modeled within the Optics Studio software package. For the system as we've built here, we were able to achieve roughly a ½ degree full field beam size over that 40-degree field of view. So this is looking at 3 different beams, effectively, which are meant to represent 3 different sources in the source array for the flash system. And you can see each of them have a really tight beam size in the vertical direction, but which are well separated as well. And this is actually a key piece, because we need to make sure that the beam, as it reaches the detector, doesn't overlap, so that we can get a discrete information about the horizontal and vertical position from each beam separately. Now we have a separate model again for our receiver optics. And again, in this case, the goal is for the receiver optics to collect the scattered light over the full field of view at the required angular resolution. The specification in this model is to have angular resolution of 3 degrees in the horizontal plane, and in the vertical plane to collect all of the light over the full field of view. This is a schematic showing the lenses that we've used to model the receiver in the horizontal plane. Again, just using spherical lenses in this particular example to keep costs down. We're actually, with this system, able to achieve a vertical angular resolution that's better than the specification. We're able to get a 1 degree field of view. You can see here from each of the diode sources being captured on the detector, you can see a clear separation between the sources, which indicates that we're able to discretely and with good definition capture information from each of the sources separately. And this is just another way to see that information, looking at the amount of enclosed energy received on the detector that you can see that energy is captured, 100% of that energy is captured for each of the diode sources before we begin to capture any information from any of the other sources. Now again, we can put information, or I should say we can put these two systems together that have been modeled separately back into a single system to evaluate the full system performance. And this is done by combining each of the individual systems into a single model and converting that model into so-called non-sequential mode of Optic Studio. Again, in this case, you can see here that now all of the sources have been modeled simultaneously in this particular case, and you can see all of those sources then illuminating the target simultaneously. The receiver then samples different parts of the target on different pixels within the detector array, and that's how we can then distinguish information about the horizontal and vertical position of that the light struck the detector, or struck the object, I should say. We can, again, one of the advantages of looking at this model in non-sequential is to then be able to evaluate the photometric results, to be able to look at the power that's received on the detector. Again, for a source at 75 watts, we can see that the total power on the detector is down in the microwatt range. In this system, we actually see that there's about 40% less power that's received on the detector relative to what we had for the equivalent mechanical LiDAR system, I should say. So in this system, we see about 11 microwatts received on the detector as opposed to 18 microwatts that we saw in the mechanical LiDAR system. So it would be a bit more sensitive to signal to noise in this case as a result. Another potential issue with this system is if we look at the actual power distribution on the receiver, you can see that it's not as uniform as we might like. We ideally would like to see a nice flat top of power on the detector. And in order to achieve that more uniform distribution, we might need to go back and redesign the receiver optics to include more sophisticated components. So things like diffraction gratings or other micro-optic components might be required in order to try and tailor the energy distribution on the receiver to be more of a flat, uniform distribution. Now, for the mechanical LiDAR system, we'll talk a little bit about how we would move this down into as-built performance, or modeling the as-built performance. So one of the first effects we might want to consider are environmental effects. Right now, the way that we could do that within the simulation is to look at how we affect both the reflectivity of the obstacles that light is being scattered from, as well as the model that characterizes the scattering distribution. The current model that's been used in the previous analyses assumes a target reflectivity that's representative of standard aluminum, as well as an idealized scattering model. But we can easily modify both of those assumptions. So within the interface of the software, we have options to change the coding on any of the components in the model, and that is what allows us to change the reflectivity within the model. We can also change the scatter model that's being employed. So from this ideal Lambertian model, we have a couple of different options that I'll go through on the next slide. And one of the points that I do want to emphasize, and I'll also bring this up on the next slide as well, is that both the reflectivity as well as the scattering models can be modified using other idealized models, but they can also be based on measured data. So we can actually incorporate real-life measurements into the virtual prototyping simulation. So this is an example. What we're going to do is, for a fixed scan angle of the system, we're going to investigate how the power at the receiver varies with this as we change the scattering model at a fixed reflectivity of 50%. So we'll start again with our idealized model as our baseline. So this is looking at a Lambertian scattering model in which the scattering is uniform across the field of view. And in that case, as we saw before, the total detected power is about 18 microwatts. If we were to change this to the scattering model to be more of a peaked distribution, so a Gaussian distribution in which we see light that's scattered primarily along the same direction that the light hit the the obstacle, then we can see that as a result, the power that's returned on the receiver increases significantly. Now, again, whether or not this kind of a peaking would occur on the materials that are in the field of view would depend on the environment in which the autonomous vehicle is operating. But it does go to show you the sensitivity that the system has to that scattering distribution. If we were to look conversely at a model in which even though there is some peaking, there's still a larger distribution of light out into larger scattering angles, but in a non-uniform fashion, this is actually a situation in which the total power on the detector decreases quite substantially. This is a situation where we're actually using measured data to model the scattering distribution. This is a measurement for brown vinyl, which might not be the most appropriate data to use for looking at the outside environment. This is actually a measurement of what you might have for material inside of the automobile, like for the leather seats or for the dashboard. But it just goes to show that you can use measurements such as these within the software to evaluate the performance of the system. Again, this is just one case where we're looking at the different scattering distributions and their effect on power or signal at the receiver. We could also investigate the effects of reflectivity in the same way, using either idealized or real data. And then the last topic that I wanted to talk about with the LiDAR system is the effect of tolerancing. And I'll spend a little bit of time talking about what we mean by tolerancing. The resolution that we have on the detector, of course, will be limited by the size that we have of the laser on the target. So, you know, how well we can resolve the objects in the far field will depend on that beam size that we achieve on that target. In the nominal system, we achieved, our goal was to achieve a beam size of about, as I said, 7 centimeters for a target that was about 60 feet away. But when we think about as-built performance, what we want to do is characterize what we'll really achieve as we start to account for effects of manufacturing and assembly in the system. Now, within the software, there are a couple of different modes that we can look at how these imperfections in the system can affect the system performance. One is called sensitivity mode. This is a mode in which we look at each of the perturbations or each of the imperfections in the system individually, but in kind of a worst case scenario. So the sensitivity results really represent kind of the worst case performance as we think about what could possibly go wrong as we manufacture or assemble the system. And it helps us identify the critical components, the components that the system is most sensitive to. The Monte Carlo tolerance analysis allows us to look at all of the imperfections or all of the perturbations to the system simultaneously, but more in a statistical manner. And that allows us to look at how these imperfections might interact with one another, and therefore really gives us more information about what we would get in a high volume or mass production environment. What we'll go through in the next few slides here are an example where we'll look at tolerancing just of the transmitter optics that were used for the mechanical LiDAR system, and we'll look at both the sensitivity and the Monte Carlo results to see what useful pieces of information those give us about this system and how what we need to think about as we're manufacturing and assembling the system. So the first thing we need to do as we go through the tolerancing is to go through just an initial setup. There's a tool within Optics Studio called the Design Lockdown tool, which is used to prepare the initial design for as-built modeling. We then need to define a performance criterion. What are we going to use as a metric to define how the imperfections or how the perturbations that are introduced as a part of the tolerance analysis affect the results. In this case, we'll use a metric that we call the geometric encircled energy, which allows us to give information about the beam size on the target. We then need to define what are the perturbation values, what are the imperfections, what are the things that can go wrong during manufacture and assembly of this system, and we need to define what those parameters are and what the range is over which each parameter can go wrong. So if the thickness of a lens can be incorrect, by how much? half a millimeter, a quarter of a millimeter, et cetera, et cetera. And so that's done here, where we've defined perturbations to things like the thicknesses, to the tilts or the positions of elements in the assembly, et cetera, going on down the line. We then can run a sensitivity analysis. Again, this is an analysis in which we look at each of these perturbations individually, and then we assume that all of the perturbations will happen simultaneously, but independently of one another. So effectively, each of the perturbations can all add together to give us the worst case scenario. What we can see from the results are some of the things that we're most sensitive to, are actually these thickness perturbations, as well as some of these element tilt perturbations. These are some of the perturbations that this system is most sensitive to. And we'll investigate this a little bit more as we get into the Monte Carlo results. But what we see is that at the worst case, that the beam size has gone from 0.02 degree divergence, which is what we had in the nominal case, and has increased by over an order of magnitude to 0.4 degree beam size. And so you can see that in the criterion, the range, the values, it can be even higher, up to a value of 0.47 degrees. This would correspond to a beam size of 14 centimeters on the target, on a target that was a distance of about 20 meters away, which is twice the design specification. So we've gone from having a system that was almost a factor of 10 better than the design out to being a factor of 2 worse than the design spec. One of the next steps that we can then do within the software is to figure out, well, what are we most sensitive to, and how do we restrict the range of allowable perturbation for those things that we're most sensitive to in order to still stay within the design specification. So whereas we may have initially allowed, and if we go back just a couple of slides here to see, where we initially allowed, for example, these thickness perturbations to have a range of plus or minus 0.2 millimeters, that was clearly way too loose of a perturbation to allow in this system. So we can let the software tell us what the appropriate perturbation range should be. And we can see that if we do this inverse sensitivity analysis, that the perturbation ranges are significantly tightened up. We see that for the thicknesses, that instead of having a range of plus or minus 0.2 millimeters, that they need to be reduced by at least a factor of 2 or more in some of these cases. Now, the challenge with doing this would be that we would have to incur more cost in the manufacture of these lenses in order to achieve these so-called tighter tolerances. And so we would need to really assess the cost benefit of whether or not it's worth doing that, having these tighter tolerances for these components, or whether we would need to go back and consider a redesign of the system in order to design a nominal system that was less sensitive to these perturbations. And so that would be a design decision that the engineer would have to make as they go through their analysis. And what I show here just as an example of from one of our partners, Optimax, which shows traditional ranges for so-called commercial precision and high precision tolerances, which show that the range of tolerances we're looking at here are now starting to fall within the precision and high precision category, which are well beyond, which I shouldn't say well beyond, but which of course incur additional cost as you go from left to right in the manufacture of these components. Now, if we wanted to get information about the full yield of this system, we can look at all the perturbations simultaneously through a so-called Monte Carlo analysis. This allows us to conduct a statistical analysis over all perturbations simultaneously. This is just showing an output of the result where we see a table of each Monte Carlo perturbation. And I'll actually show a brief video in a moment which shows how to generate these results within the software. And then we can look at this in a more statistical manner, and what we find is that from the Monte Carlo analysis, even using the precision tolerances that our inverse sensitivity analysis gave us in the previous results, only 75% of the Monte Carlo runs fall within our specification of 0.2 degrees. there's a long tail to the distribution, you can see. So many of the runs do fall within the specification, but there's a long tail to that distribution of runs that do not. So again, we would need to consider whether the appropriate design choice would be to increase or to tighten the tolerances even further, or to go back and consider a redesign of the nominal system in order to improve the performance relative to the as-built specification. So this is just a brief video which shows the generation of those Monte Carlo results within the software. This is through a tool that we call the tolerance data retention tool that we have within the software. And we can see that in this case, we're setting up the system to do 400 Monte Carlo runs, but that number could actually be significantly larger if we wanted. It's just really a function of the amount of time that you wish to spend. For 400 runs, we can generate this data almost instantaneously, and you can see here then results for each of these Monte Carlo runs, and those results then generated easily exported to Excel to generate the statistical analysis that I showed previously. But again, if you were willing to invest a little bit more time in this analysis, that number of Monte Carlo runs could be increased to the tens of thousands, hundreds of thousands, or even larger. The last thing that I want to dive into with the mechanical system are just to talk about the effects of optomechanics, because everything that we've been talking about to date has really been just looking at the optics themselves. But of course, these optics are going to need to be in some kind of a housing or packaging system. Zemax offers a tool called lens mechanics, which can be used to import the optical design directly into SolidWorks or Creo Parametric, where the mechanical engineers can then start to add the optomechanics, the mechanical housing and packaging to the system. Lens mechanics has a great benefit in that there's no need to translate the optical components to CAD. Those optical components can be read directly into the software, into the CAD software through the lens mechanics add-in. And then within lens mechanics, we offer the ability to look at sensitivity to things like system wavelength, which is what we're trying to show here, where the mechanical engineer could actually probe different wavelengths in the system, can change ambient conditions as well, such as system temperature, pressure, etc., and that can all be investigated. The real key value of lens mechanics is that you can actually do optical ray tracing within the CAD environment. After import of the optical components, just to evaluate how that import has worked, but also as mechanical components have been added to the system. So this is just a screenshot which is showing a ray trace in action, so you can see that we're actually running a ray trace. It's in progress. It's been about a minute here, where rays are actually being traced through the system to evaluate the optical performance of the system inside of the CAD environment. Once that ray trace is complete, you can actually see those rays within the layout plot. And again, zooming in here on the housing of the transmitter and receiver optics, you can actually see those rays being illuminated from the transmitter, being collected by the receiver, how those rays might interact with the housing or the other mechanical components in the system. So lens mechanics in this case really has an important key value in the design of this system, because you can really begin to account for the manufacture of the system and how that manufacture will impact the performance of the system. Just finally, I want to just talk a little bit about what I envision as some next steps for LiDAR. Some of the things we haven't talked about in this webinar, but will of course play a key role, are structural and thermal analysis of the optics and the optomechanics. These can include changes in the ambient environment, and whether they are transient or steady state, doing an analysis of wear and tear over the system lifetime as well. And Zemax is currently working on tools to allow data from finite element analysis programs to be imported back into Optics Studio to be able to do this kind of analysis of the structural and thermal impact on the system. Also, if we think longer term in terms of how LiDAR can be impacted by some cutting-edge technologies, machine learning is a technology where we can think about training systems, detector systems, to recognize common objects or recognize common signals to try and improve the efficiency of those systems and increase that signal-to-noise ratio that right now is very, very small for these LiDAR systems. So just in summary, LiDAR is a critical component for autonomous vehicles as we move from level 0 to level 5 of autonomy. But no clear solution has yet been identified for LiDAR systems for all cases. And that's where virtual prototyping can play a key role in helping with the identification of those systems. Cost of these systems is going to be driven by complexity as well as performance requirements, but also by the ability to get these systems into mass production. And as I mentioned, virtual prototyping really offers a quick and efficient means for exploring existing solutions and identifying new solutions for LiDAR that can be mass produced. As we go through virtual prototyping, we need to understand both the optics as well as the optomechanics, and we need to understand the performance of these systems under nominal or ideal conditions as well as built. And then finally, just want to leave with the fact that companies which are using virtual prototyping are really those companies which are leading the industry in the design of cutting-edge, state-of-the-art LiDAR systems. So with that, again, just an introduction here to the two software packages that are part of the Zemax software suite, Optics Studio and Lens Mechanics, and then hopefully some time for questions. And thank you for your attention.
Thank you very much, Sanjay. And I am going to take a couple of questions here, even though we are drawing close to the end of the hour. So the question is, what is the measuring range of an automotive LiDAR system? I mean, distance measurement.
So again, generally the range that these systems need to be operating in tend to be between about 100 feet to about 300 feet. So those are the objects, that's the distance of objects that the LiDAR system is meant to detect. So hopefully that answers the question there.
Could you comment on the type of laser required for each technique, edge emitter versus VCSEL?
Yeah, that's a good question. So in these examples that I've shown here, we've been looking at traditional diode sources, I guess more traditional VCSEL type sources. Certainly, as we look at trying to increase efficiency of these sources, we might be starting to look at whether LEDs or edge emitters or other types of sources might be more beneficial in those regards. Again, the benefit of virtual prototyping is that you can do that evaluation. You can swap out these different sources and see the impact within the simulation. But I think for now, just given the prevalence, ease of use, and the ability to get to the required power of these systems, we've been looking at more traditional diode laser sources.
Okay, thanks. Is there any information on which wavelength is better from the target of interest reflectivity perspective?
Oh, that's also a very good question. Generally speaking, the shorter wavelength would have a higher typically have a higher reflectivity. And so the 905 nanometer wavelength would tend to give you more signal than you might see at the 1150 nanometer wavelength for the same power of laser. So again, you'd want to use shorter wavelengths to try and get more power. The disadvantage, again, is the safety considerations that you'd have to take into account.
Okay, thank you. To have enough rays come back and get collected by the receiver lens, it would require the model to send out orders of magnitude more rays, worse at long distance. Mm-hmm. How does that affect the model speed?
Yeah, no, that's actually a really good question, and it's not something that I had time to get into today. But one of at least within the model, again, since we're modeling light as being scattered from these objects and returned then to the detector, we can take advantage of a capability within Optics Studio that's called importance sampling. Importance sampling is a capability by which we can actually specifically only try and collect rays that we know are going to make it to the receiver, and we can attenuate the energy of those rays according to the solid angle that the receiver makes compared to the objects that are out in the field of view. So to try and put it in a more layman term, if possible, there is a capability within the software to filter for those rays to make sure we only are going to collect the rays that would actually make it back to the receiver, and therefore be much more efficient in how many rays we need to trace to the system. And so certainly if you have questions about importance sampling, we have some nice information on the Zemax knowledge base about that, that might be useful information for you.
Okay, I'm going to ask just a couple of more questions here. How does the weather condition, for example, rain and snow, affect the LiDAR accuracy?
Well, certainly, I mean, one of the big challenges with weather conditions will be transmission efficiency, right? So as you get through rain and snow, the ability for the light to be transmitted through those conditions and back to the detector are going to be affected, and so you'd expect to see lower signal and more noise on the detector, which means you'll need to have higher power lasers under those conditions. Now, there is one consideration to think of, is that LiDAR, of course, is just one part of the entire autonomous vehicle system. And so as conditions like, especially as we think about snow and blizzard conditions are in play, of course, we would want to not be out in general in a vehicle. And so, the ability of LiDAR to perform under those conditions almost becomes secondary to just vehicle safety in and of itself. But certainly as we have the impact of weather, we have to think about whether we can deploy higher laser systems in order to be able to combat that. And those may be conditions in which the continuous wave lasers may have a benefit, because we do have the advantage of having less background light and being able to filter more effectively for background under those conditions.
Okay, thank you. And this question is regarding the Zemax product. Could we export design from Zemax in a *.stp file?
Yes. So this is what's being referred to here is a CAD format that sometimes is also referred to as step format. So yes, Optic Studio does allow you to export designs into a step format. It's a capability just within the software itself. One of the advantages of using the lens mechanics software is that you don't need to do that, because you can bring your optical design directly into the CAD platform without going through that conversion process. But if you needed to export to STEP or IGES or STL or SAT formats, which are all common CAD formats, that's all supported through the Optic Studio software.
And can we trial the software?
Yes, that's a great question. If you go onto our www.zemax.com website, you should be able to see a link in which you can request a download, and you'll just have to fill out a small registration page, and then we offer downloads and free trials of the full access to the software through that registration.
Okay, thank you very, very much. And at this time, I'm going to close the webinar. A recording of the webinar will be available shortly, and everyone who attended today will receive a link to the recording tomorrow in a follow-up note. And please email the moderator if you would like to receive a copy of the slides. I would like to thank Zemax, our speaker, Sanjay Gangadhara, CTO and Head of R&D for Zemax, and all of you for participating in today's webinar hosted by Photonics Media.